In this tutorial, we're looking at a node, or rather a pair of nodes, called Foreach loops. This is a way of inputting geometry and looping it around several times, either per piece or per point or per primitive, or simply taking a set number of loops and passing the geometry in a circle, performing an action on it each time. Originally, this tutorial set out to look at the copy stamp node, which is something that a few people have asked me about. When I started doing a bit more research into it, I realised that the most recent documentation from Sidefx recommends that instead of using copy stamp, you use a Foreach loop, which it says is more efficient, easier to set up, and easier to understand. I definitely agree with the last two. So what I'm going to do is give you a quick run over the copy stamp node, because you'll hear about it and you'll probably come across it, and you might actually prefer it. And then I'll spend the rest of the tutorial looking at the Foreach loop, which can do everything the copy stamp can do, but an awful lot more. So first of all, I'll explain about copy stamps. So I'm going to drop down a piece of geometry. And I'm going to create a grid, and we're going to use the points of that grid to place objects. So the copy stamp node in many ways is very similar to the copy to points node, which allows you to place objects and points, but it gives you a bit more functionality. So if we take a look at it, it sits just above copy to points, and in fact it combines some of the functionality of copy to point. So if you look in here, you can set point attributes in the same way you do with copy to points. It also has the functionality of the copy transform node, which allows you to make copies and add progressive transforms to them, which is a bit more straightforward. So you'll see it's quite similar to the copy tab. And finally, it has the stamp functionality. And what stamping allows you to do is take attributes from your points, so in this case the points on the grid, and filter those attributes back up the input line and apply them to the input geometry. It's a slightly odd concept to get your head around, which is one of the reasons why Sidefx recommend the Foreach loop instead. It's actually quite straightforward, so best thing to do is go ahead and set it up for you. So we'll plug our grid into the second input, which is template copy 2. So this is where our points are coming from. And then into the first input, I'm going to go back and use the digital asset which I created in the first tutorial, low poly tree. And I've actually updated this a little bit to apply custom color, because I think, well, for a start, I've used that quite a lot in tutorials since, and also it's quite useful to illustrate here. So if I turn that on, I can apply a custom foliage color without coloring the trunk as well. If I turn it off, then that's just random. So the way this Houdini digital asset works is you give it a random seed and it gives you a slightly different variation on trees, and the seeds are input as integers. So in here we have an option of 1 to 100. So I'm going to plug this into my first input on the copy node, and you can see it's created a bunch of trees lying down. So first thing we want to do is transform that. Let's see if we can do it by setting the point attributes. No, that's not going to help. So I'm going to put a transform in here. And we'll rotate this by 90 degrees. So now all our trees are pointing upwards. Now I'm going to set up a basic copy stamp to see how this is done. So first of all, we select stamp inputs, which enables it, and then we set up variables. So these variables can be read by any of the nodes upstream of the primitives to copy input, and the values read in the values from our template to copy to input. So the variables, we just give it a name. So I'm going to call this seed, because what I want to do here is take a variable using the point number from our grid and use that as a random seed to randomly generate some parameters coming into the copy node. And therefore I'm going to give it a value of @point number. So for each of these, if we take a look in our geometry spreadsheet, these are our point numbers. So each of these points now has a different value, and we can use those different values when we're creating our input. And the way that we access this is we use a expression called stamp, and if you type in stamp and then open brackets, it will give you the syntax. Takes 3 inputs. The first one, you have to point to the copy node so it knows which node to look for. So to do this, we well, there's a couple of ways we can do it. We can actually just drag this in. See if I can do that without having to overwrite it. No, it's not going to let me do that. Okay, I'm going to do it the other way, in which case we go up 1 and then find our copy 1 node. We surround that in inverted commas, and then the second input is our token, which is actually the name of our variable. So again, inverted commas, we type in seed, and then the third value is just the value to use if for some reason it can't find a value in our stamp variable. So generally that would be 0. You can make it anything you want. The main use of this is if there's something going wrong, you can change this value and see if all your input values are coming from here rather than from whatever you've told it to bring them in from. And you'll see one of the problems with this setup is, which we'll find a solution for in a minute, is the fact that every time you change the random seed value, it has to run through the entire network inside this Houdini digital asset, which is quite slow. But you can see it's worked. So we now have a bunch of trees that all have a different type of tree on them. And in fact, see how many points we have on this. Yeah, so we have 100 points. So in fact, this would be a nice little demonstration of all the different tree shapes that we have in our 100 variables, because they are going, let's turn this on. So starting here, they're running along each row and being laid out from 0 to 99. It's probably not what you want. For a start, as you saw, it was very slow because we're doing a lot of calculations. And although in this case there's no relationship between the types of trees that are closer to each other in value, in other instances we might want something completely random. In that case we would stick a rand function in here. And this, I think if we let it run through, I think this is going to now give us a value from 0 to 1, which isn't what we want. We'll probably just get one type of tree, or possibly two. Yeah. So we need a fit01 expression, and then we can give it two values to output. So we want to go from 0 to 99. And now we should get all our different trees back again, but this time they won't run from in neat rows anymore. They'll be completely randomized. The randomization you can either put in at the top here, or you can stick it inside your value in the copy node. So we could be randomizing at this stage. I think it's slightly easier to set it up this way, and then you've got a nice simple relationship and it's easy to see what you're sending back up the chain. Also means that you can play around with it in different ways once it's up here. I do actually use the copy stamp node in the first tutorial of this series. So if I open this up, if you go to the first video you will be able to download this scene, which you see is a reasonably complex setup, and this is where all the pieces are brought together. And you see I actually use a collection of copy stamp nodes which take variables from the surface that's input. So this is the input surface. In fact, these are the points. This is the input surface. And then I scatter points on it. Points aren't terribly easy to see. There we go. And these points have variables on them. And I want to use some of these variables in the objects that I'm placing in these points. So, for example, on pieces of grass. So, in this case, I'm using exactly the same method. I'm using a seed, which is generated by a point number in here. And I'm using that to vary the colour of the grass randomly, but keeping it within certain parameters so that it's always a shade of green. So you'll see when the grass is placed, it has a variety of shades of green. The second one looks at density, and let's have a look. So the density I have linked to a variable called size, and in this case I think I've linked it to the height of the grass. No, the rotation of the grass. No, the rotation of the grass is a random seed. The scale of the grass is affected by the density, but I think it's quite subtle. The idea is that the grass in the thicker areas is a bit longer. So you can open up this scene and have a look at the way I've used different variables back up the chain to affect the placement of objects. But now I'm going to go back to this scene and show you how to do it again, this time using the Foreach loop, which isn't any easier to set up, but I think it's probably a bit more straightforward to understand. One more thing that might be quite useful for you if you do decide to use the copy stamp node is that it has some great examples with it. So if you open up the help documentation for this node and go down to the examples, there are a couple called stamp random and stamp stars, and they're both really useful examples of how to set up the copy stamp node, and particularly stamp stars, which is shows you how to use a lot of different variables. And I usually go back to them if I'm using copy stamp and it's not doing what I expected. I'll go back and take a look at these and compare them to mine, and it's usually pretty clear where I've gone wrong. Okay, so now we're going to take the exact same inputs, so we'll copy these over. Which it's taken quite a while. There we go. Let's do that back. And open up the Foreach Loop. Now, if you type in Foreach in your nodes list, you'll find that there's a big list of possible nodes. In fact, these are all exactly the same nodes with different setups. These options make it a bit easier for you to set them up, because they're preset to do to use the geometry in different ways. So we're going to use this for each point first of all. We can just take this loop and change it to any of the other ways of using it. I'll show you how to do that. So what you get by default is two nodes. So we have an input node, the begin node, and we have an output node, the end node. And anything that you want to be repeated inside your loop goes between these two nodes. And in this case, what we're going to do is we're going to take every point from our grid, cycle through each point one at a time, so we can do any nodes that we want to use on each point we put inside here, which in fact will be these nodes here, because we're going to be copying onto these points, and at the end this will collect them all together and output them. The settings that make it run through our points are the method here, which fetches each piece of point. There are different ways of doing this. If we set it to fetch input, it'll just take the input as a single piece. If we set it to fetch feedback, then at the end of each loop it will take what it's done and put it back round again. But for the moment we want piece of point, and you'll see in the end loop we need to set this as well. We have our iteration method by pieces or points, so again we need to set this, and then we have our piece elements, which are our points, and then we have our gather method, which we can either set to feedback or to merge. In this case we want to just perform this on each point, then merge the whole lot of them together and output them as a single object. So the default settings, because we chose to set it up for points, are exactly what we want. So we plug in our grid. There are some, in the end node there are some settings that can be really useful for debugging what's going on. So we have the single pass option, which just outputs a single point. So if I switch this on, you should be able to see it. There, that's point 0. So what we're getting here is our loop simply going through one point and then stopping, and we can actually change which of these it is. So if you're having a particular problem, this is a really good way of seeing what's going on, and you're just working on a single point, and then you can look at all the settings inside and see how they're affecting that point. If we turn this off, it runs across every point and outputs the whole lot. In this case it's not doing anything to them, so what we're getting out is the same as what we're putting in, except that because we're filtering out points, we're only getting points at the end of this. So what we want to do with each point is copy our tree onto it. So we'll just go back to our original copy to points node. and we want this to go inside our loop here. So first of all, we input our points into the top, and then we output the copied object into here. Transform seems to be working on this one, so, or rather the tree position is working, so we don't need the transform. Okay, now if we go back to our single pass, we can now see the output of a single point, and you'll see that for each loop, so in each pass, it's taking the tree and copying it onto one of the points, because we're only running one point at a time. The advantage of doing it this way is that we now have access to each individual loop. So any variables that are attached to the points we can take and apply to each individual tree. It's just a slightly more intuitive way of looking at it. So rather than taking everything at once and dumping it on, and then taking some arbitrary value and applying that to the input, what we're doing is just running through these one at a time, and each time we run through them we can access any variables in those points and use them to apply to our trees. However, one disadvantage is because we've separated out all our points, we can't use our point numbers anymore. So if we turn on our point numbers, and I'm just, can I see it in here? Yeah, there we go. So here we're just seeing the one individual point. And if we step through, one thing you might have to do is, to see an update, you might need to switch to the end node and then back again. But you can see the value of this point, no matter what pass we're on, is always 0, because we've only got one point, so it has to be the first point value. So we can't use our point number attribute anymore to generate our random seed that we're going to apply to this. So we need a way of accessing a changing variable as it goes through the cycle. There are a number of different ways to do this. We could create a new variable. In fact, that's probably the simplest way to do it. So, at least the simplest way to understand. So if we create a new attribute, and we call it, let's call it seed, and we just make it a, well, we want it to be an integer, and we'll give it the value, oops, a value here, not a default, of at point number. And now if we open our geometry spreadsheet, we've applied a seed attribute, which is exactly the same as point number. And now when we go through each point, let's go back to top node, so we're just seeing one point. We should, but don't, have a seed attribute. I think this just needs a refresh, so if we go to the end, our seed value is coming through, and back again, so we now have a value of 1. So here we're seeing a single pass of 1. If we change this to 2, we're now getting a seed value of 2. So now we have an individual value on each point. So let's go to our scene view, and now we can use that seed value in our tree. Now it's not immediately apparent, but this tree is actually part of our input and output node, because it's now being input into a computer points node. It's a slight bug that the interactive outside edge of the for each node is not encompassing this, but it is actually now part of this loop. So we can use our seed attribute. So here we can probably just adapt this, so we don't need our stamp anymore, and in this case we want at seed, except seed doesn't exist in this object, so we're going to refer to the point value in our first node. So we want the point expression, and to use this we give it the node, we give it the point number. In this case the point number is always 0, as you've seen each point is called 0. The name of the attribute and the index, so if it was a vector with 3 variables, then you would use 0, 1 or 2 to point to each of those variables. So in this case we want to go to the for each begin node, which is a slightly clunky thing to have to type in, and then we want the point number, which is 0, and the name of the attribute, which is at seed, and then finally, because it's an integer and it only has one variable, we use 0. And let's see if this works. We seem to be getting a random value. At the moment we're only running a single pass. It does look like all our trees are identical. I'll run this once to see how long it takes, and then so currently not working. I'm going to reduce the number of rows and columns so it runs a bit faster next time. Okay, so we've limited our number of trees. So we'll see what the problem is here. I think it is that we don't need that at symbol for the name of our attribute. There we go. So now we're using our seed attribute to create a random variation for each tree, and this network is now working in exactly the same way as this one. Let's reduce our grid for here as well. So the effect is pretty much the same. It's really up to you whether you think the first or second one is easier to understand. If you're working with large networks, Sidefx say this is more efficient, so it might be better to go with this one. I also think because the for each loop is so powerful, it's good to get working with it and understand how it works and make sure you use it, because there's so much you can do with it. Now I'm going to show you a different way of doing this, which is probably more standard really. So rather than creating an attribute called seed and forcing it to be unique on each point, there's an option in our begin node to create a meta import node. And what this does is it creates a series of attributes as part of the loop and puts them on each iteration of the loop. And the attributes are iteration, which is the one you'll use most. It basically goes up for every loop. So in the case of the points, it would end up being exactly the same as the point number you're putting in. So the first one would have an iteration of 0, and then the second one would have an iteration of 1, and so on. So you can access this instead of using point number. Second value is a constant value for the complete total number of iterations, and let's have a look. I'm going to check here what the attributes of value and I-value are. So it looks like the value gives you something similar to the iteration. It gives you the value for each piece that's being input. Let's quickly set this up. So in our low poly deciduous tree, rather than referencing our seed here, we reference this loop. So the for each begin one metadata one, which is an even more clunky name to input. And instead of seed, we're going to use the iteration. And one more thing to change is this isn't a point attribute anymore, this is a detail attribute. So instead of point, we put in detail. And the detail attribute doesn't need a point number because it doesn't have one. So we should, I'll just check this is correct. For the detail, we should have the node that we're referring to, followed by the attribute name, which is iteration, and followed by the index. So that should work. Go back to our scene view. And yep, we're getting exactly the same result. So we can now delete this attribute if we want. So that's two ways of setting up a simple for each loop to mimic the copy stamp node. I think if you're trying to do something quite complicated, it's probably easier to do this this way because it's a bit easier to understand what's going on. Next I'm going to look at some of the other things you can do with the for each loop. Actually, before we go there, I did say I'd show you a way of making this a bit more efficient. So the reason that both of these methods are slow is actually the fault of this Houdini digital asset. If we open it up, you see there's quite a long network inside here, and it's doing quite a few things, such as converting it to a VDB and back again. The way that our network is set up means that for every single loop, so in this case 16 loops, it's running through that entire network. So it's running through that network 16 times. So you can see why when we've got it running through 100 times it's pretty slow. You probably don't need every single variation on this tree. So a much more efficient setup, let's do a copy of this, which again will be a little bit slow because it has to do all the calculations again. So a more efficient way of doing this would be to set up a switch node, which I think is the way I actually did it in the first tutorial. And we take this value off here and stick it on our switch node. And in this case we want our highest value to be the number of inputs, so it doesn't need to go as high as 99. Let's just give it 5 different variations. So our random input here should go from 0 to 4. So now we'll remove our random seed. The other advantage of doing it this way is you get to pick 5 trees that you particularly like. So now we have our 5 inputs. I'll stagger them slightly so I can see them. And plug them all into the switch node. And then we'll just change our random seed. We can have a look at these trees and check that they're suitable. And now when we run our nodes again, we're getting random variations between these sets of trees. It looks like we're getting an awful lot of this one for some reason. Good way to check what's going on here is go to one of these trees, go to our switch node, and we can see which value we're getting here, which is number 4, 0, 1, 2, 3, 4, which is this tree. Let's go to a different value. Again, we're getting 4. I wonder, is it just coincidence that we're getting a lot of 4s? It's possible. Random generation can be a bit strange. One way we can change that is we take our detail value, which is what we're using for our seed, and just change it slightly. If we add or multiply this by a small number, it will just change it very slightly, which means that all the random numbers are completely reset. So let's add 0.1 to it and see what happens. Yeah, that looks a bit better. I think we were just getting a slightly odd occurrence of that tree randomly. So this is a much faster way of working because our each of these is only calculated once, so that these objects are now effectively outside the loop, and what we're using here is just a switch between each one. So we should be able to increase our rows and columns back up to 10, and it should run a bit faster. Yeah, so now it's generating that quite quickly. You're not getting a massive number of trees, but you can keep adding here. You could, if you wanted, put all 100 trees in there, and it would still be a bit more efficient. Now I'm going to show you a slight variation on this, which allows you, rather than looping through individual points or primitives, to separate them out into groups. So if you go into the menu and type in Foreach, this is the option that you get if you go to for each named primitive. So if we drop this down and compare it to our original piece, this input node, the input node is the same, but on the output node we have an option ticked for piece attribute. By default this will give you primitives, but it works equally well with points. And what the piece attribute does is it takes everything that has an attribute called, in this case, name, but you can change it to anything you want, and where those values are the same, it puts them through, puts all those points or primitives that have that value through in the same loop. Probably the best way to show you is just to make a copy of this one, because it's quite a subtle change. And you can see the difference. So first of all, we'll just change our setting and we'll give it a piece attribute. In this case, I'm going to call the attribute style, which I think is what we used before. and disappears because we don't have that attribute. I imagine we'll get that error there. Yeah, invalid attribute. So we need to create that attribute on our input grid. First of all, let's increase our resolution a bit. Now that we're just putting a limited number of options in, this can run a bit faster. So we can increase our resolution. And then I'm going to create a point attribute using an attribute bot. And use noise for this. Let's go for a nice simple anti-alias noise. Hook that up to our position. And easiest way to check what's going on is to stick it in our colour. So now you can see we've got some noise. I'll decrease our frequency a bit so it's a bit clearer what's going on. And then we want to create a new attribute which is called style. So we'll put in a bind export. And call this style. And in this case we want it to be an integer because we want a limited number of values. So we don't want every gradation of grey across our noise. We just want a set of discrete values. So if we open our geometry spreadsheet, and take a look at that. This is, although I've told it to be an integer, it's still taking the values that are input to it. So if we remove that, okay, so now we're getting values of 0 for everything. If we look at our colour values, which are, you can see the original float input, you'll see these run from about 0.2 to about minus 0.3, and both those values will be rounded to 0. So what we want is a fit range node to extend those values over a bigger range and hopefully give us a larger range of values here. So let's make our maximum output 5. We want that to go from 0 to 5. And we'll take our source from our values that we're getting coming in. So we want to cover the full range, so we go from minus 0.3 to 0.3. And we're still only getting zeros as a value. Oh no, we're not. So yeah, now we're getting across the range. So now we can use these style values. So if we look in here, you see we've got a point attribute called style, and we can use that in our loop, which you can see has immediately done at least something for us. Looks like it's probably working correctly. Let's just run a single pass till we see what's going on. So if we this is taking the colour from the point, so I'm going to unhook colour here and see what's going on a bit more clearly. If we just run a single pass, you'll see that instead of just one tree coming through, it takes through a whole group of trees. And these trees are each being assigned a different value from our switch value. So we have 0, 1, 2, 3, 4. We have the correct number of trees coming in, so we go from 0 to 4 here. Sorry, it's the style that we're looking at. And we need to be looking at the input. Yeah, so we're going from 0 to 4. And every time it runs through, it's doing exactly the same as we did last time, and it's putting a different kind of tree onto it. But this time, instead of 100 or more loops, it's just doing 5 loops, so 1 for each style. So as you can imagine, this is a bit more efficient, and it gives us a bit more control as well, and it allows us to play around with some different ways of splitting up our objects and accessing the geometry inside them. If you type in Foreach again in the menu, there's also an option called Foreach connected piece, and this will set up exactly the same loop as for each named primitive. But this time it sticks a node in front of them called connectivity, and what connectivity does is takes your points or primitives and splits it into groups that are discrete. So if you imagine a number of discrete spheres, even if they're part of the same object, it will split each of them into a different group and assign an attribute called class with a different integer. And what this does is basically sets up the correct parameters for your loop without you having to worry about it. So I'll show you an example of how this would work. In coming up with ideas for examples, I've realized that this functionality is the separating out pieces through connectivity is actually built into a lot of the Houdini nodes. So a lot of things I thought would make good examples for you, you actually don't need a loop. So one example I was going to use is the measure node. It's probably worth showing you how a different way that we can use these pieces. So I thought it'd be quite useful if we have an object broken up into small pieces to be able to measure the area of each of those pieces rather than measure the whole thing. But if you actually look here, you can already do this by setting up the per piece attribute, and then in the same way that connectivity creates an attribute called class, this will use the class attribute to split them up. So effectively we're making a little loop inside this without having to worry about it. So I'm going to show you something a little bit more complex. First of all, you don't need to worry too much about this because we'll cover it later, but we're going to look at a node called Voronoi fracture, which is something that you'd use in destruction if you want to break an object into reasonably natural looking pieces in order to break it apart. It's a good way of separating something out into lots of pieces. It takes 2 inputs. First one is the geometry that we want to cut up, and the second one is a group of points on the surface. So let's create a sphere and make it a polygon mesh, something a bit bigger than that. And then we want some surface points, and the easiest way to do that is to use a scatter. Now the number of pieces we get is determined by the number of points, and we don't want that many pieces, so let's take our total count down to about 7 or 8. And now you can see we've separated our object into some separate pieces. It isn't terribly obvious yet, but it has in fact created some pieces. Now by default this will create pieces, however these are groups. What we want is a attribute with different values, so we still want to run it through the connectivity node. Let's hook it up here. So, oops. Now if we look at our geometry spreadsheet, we've created an attribute called class, and it's got a bunch of different values for so each primitive that belongs to a single piece has the same value, so there will be 8 pieces here. Now what I want to do is take each of these pieces and write my name on it, and I'd want to do that I want it to be orientated in the direction of the piece, so it's actually written clearly across each one. I'm going to use a node called font, which allows you to write some text. And I'm going to write my name in here. What this does is creates a little bit of text using nose curves. It's probably a bit on the big side, so we can make it a bit smaller. We can neaten that up later on. And then for each piece, so you can see here we've now got a bunch of pieces. I want to project my name onto it. I don't actually need this inside bit here, so I'll go back up to my Verona fracture and turn off create interior surfaces. Just won't actually update until I hit the end node. There we go, now it's just the outside surface. So in order to position my font, I want to find the center of each of those nodes, or of each of these pieces, and there's a way to do this quite simply. Go to extract centroid, and we want to run over the detail, so that means we just do it once for each piece and output a point. So for each piece, so if we take a look here, do a single pass and run through the pieces, you'll see we've created 1 point, and each of those should fall near the center of the piece. The other thing we want to do is orient it correctly. So for this we need a normal. We want to set the normal up on our piece. So let's create a normal. I'll assign it to points. And then we've got our centroid, and we can use our attribute transfer node to put our normal onto our centroid. So now you can see the normal direction is roughly the same as the surface that it's closest to. And the last thing we want to do is copy our font onto those points. So we just use a copy to points node. It's only a single point. So now we've got our font correctly aligned, and then we extrude it using a poly extrude node. Let's give it a distance of 2 just to make sure it goes far enough. In fact, let's make it 10 because we might have quite a big sphere. I don't need our normals anymore. And now I'm going to use a boolean to subtract that from our surface. We'll stick our original surface in here and subtract our extrude. Looks like that's going the wrong way around. No, it's because we've intersect. Let's subtract. There we go. So now I've subtracted that from my face, and let's run it over the whole thing. Booleans are quite slow, so it takes a little while. So now you can see each face has my name written on it, and it's all oriented correctly. If we wanted to be a little bit more clever, we could add our metadata import node in here, and now we have iteration attribute under our details for the number of passes. So in our font here we could write piece, and then we use the detail node and we reference this node here, which we can drag in. The attribute called iterate, and it's a single value, so we just stick in 0, and the little dashes at either end tell it to evaluate what's inside here, so it will work that out and then add it to piece, and that seems to be working because it's taking its time again. Except we have the same value for each one. Let's see what's gone wrong. Oops. Yeah, it should be iteration rather than iterate. If you want to check if it's not reading things properly, an easy way to do it is to change this value, which is the default that it uses if it can't find anything. No, I'm wrong. This is just accessing the first variable. So let's change this to iteration. It's cooking again. There we go. So now we have the correct piece numbers written on each piece. The last kind of loop that we can do is probably the most straightforward. It simply iterates through the loop for a set number of times, and you can choose either to feedback the information and keep adding to it, or you can just feed it back and keep adding to the same object. I can show you a simple example. If we go back to our sphere, let's just make a copy of it. We don't need it split up anymore. And once again type in for each for our loop, and this time we just do for each number. This time it gives us our metadata by default because I guess I reckon you're more likely to want it in a fairly straightforward loop to be able to access the number of times that the loop's been passed through. Oops. So our iteration method is by count rather than by pieces or points, and then we have a number of iterations which we can change to anything we want. And here we have our method as fetch input, which is very straightforward. That's just going to be taking our input, and then we can do something a set number of times to it and then output it again. You're more likely to use the fetch feedback option, which rather than just using the input once, will actually take what you get out here, and then on the second loop round we'll put it back here again. So anything that you apply to it keeps building as you go on. And in this case you either want to merge each iteration, in which case for every loop you get an individual output, or you can feedback each iteration, in which case the same piece of geometry will go round and round. It's probably easiest to show you. So if we hook up a sphere, I'm going to stick in a mountain node. and it's kind of hard to see what's going on here because it's on the same place, so I'm also going to put in a transform node and offset everything. So we'll translate this. So now you can see what's happening here is every time we go through this loop, it's offsetting our points by some noise in the mountain node, and then it's getting to the end and feeding what we've got out of it back in again, but it's also including our original sphere. So every time we loop round, we get an additional sphere, and you can see the ones that are there from the very beginning. The amount of noise distortion on it has built up until it's quite spiky. If we go to feedback each iteration, then it just keeps going around in a circle with the same piece, and this is, well, certainly the one that I use the most often. So you're simply running one piece through the loop for a set number of times. I don't know, it's worth showing you a specific example of this. It's a very straightforward thing, and it's actually quite hard to find examples of for loops because they tend to be either something that's really so simple that it's obvious why they're there, or they're integrated into such a complicated network that it doesn't make a lot of sense. I find that I use loops constantly when I'm creating networks, but at the same time it's quite hard to remember exactly the situations in which I would use them because there are so many different situations where they're useful. One thing that is worth showing you is that a loop, these nodes in the loop can be nested inside each other, and there are actually some quite complicated networks that can be set up. So you can have one piece of geometry entering a network for a set number of times, and another piece of geometry entering a network as a number of pieces. Although these seem like they're horribly complicated to set up, they're actually a bit easier than you would expect. Possibly the best example to show you for a more complex network is the Sidefx Swiss cheese example, which you can see if you load up the help documentation, and you can load it into your scene as well. So this is the documentation for the input node for your Foreach node, and down the bottom here there's Swiss cheese, which I will load into this scene. But if you go to their link to their documentation on looping, I'd recommend reading all this anyway because it's a complicated topic, and they cover it in lots of depth, but it also specifically outlines exactly how the Swiss cheese example works. So you'll see some of the examples that are similar to the ones I've given you. And then we have the multiple inputs, which shows you how you can have two different input nodes on a single loop. So we have two start loops here. I'll just quickly take a look at Swiss cheese. So what this is doing is taking a block, which is actually quite low polygon. Let me reduce the voxel size a bit. And then takes a group of spheres and progressively subtracts each sphere from the voxel block. Yeah, so I'd recommend you take a look at that. I'm going to finish off with a look at fractals, because the Foreach loop can iterate progressively over things and feed them back. As you can imagine, this works quite well with fractals. So this fractal example I'm going to show you is actually very straightforward, and it just uses a simple count loop. So first of all, we're going to create a circle, which is a NURBS curve that sits in the circle. And at the moment it's in the XY plane, which should work fine. Let's make it a polygon, and just hide our Swiss cheese. And now we want to select every other point because we want to make it into a star. So we'll use a group range node. Select points and select every one of 2. So you can see we've got every other point selected now, and then we just need to transform those points to make it into a star. So we grab group 1 and skip. We're getting a bit of odd folding here. You can fix that with a try divide node. There we go. So now we've got a star as an input. And what we're going to do with our loop is take every one of the points on the star and add a smaller version of the star, and then repeat that again. So we start building up a fractal style pattern. So let's go straight into our loop, and we'll do for each number. In this case we do want a metadata node, and we're going to be feeding back each iteration because we want all our stars to be visible, so we want to see the original one that comes in, and then the smaller ones, and then the ones that are even smaller again. So we'll feed back, and in this case we'll fetch feedback. And then all we're going to do is create a copy to points node. And we'll take our sphere, which we're bringing in, and copy that onto the sphere. So let's drop down our iterations. It's going to be a bit difficult to see what's going on. Well, even like that, it's quite hard to see what's going on because we've got a huge number of big stars. So the other thing we want to do is make them smaller, and this is where our number of iterations comes in. So we'll stick another transform node in. Like I said before, there's a bug that doesn't recognize if you're accessing this node from another one, it doesn't realize that it's part of that loop. But you need to be aware that this actually transform node will now actually sit inside the loop because we're referencing our metadata. So in our uniform scale, we're going to use this metadata node, just dragging it in as a shortcut for having to type it out each time. So here we want detail because it's a detail attribute. Stick this in inverted commas, and then iterations. I think it's iteration. Yep. And then 0. So now we're actually scaling up each iteration, which is the opposite of what we want. So let's do 1 divided. Right. And this time our stars are getting slightly smaller. It's a little bit easier to see what's going on. We actually want them to get quite a lot smaller with each step. So I'm going to use the power function. So let's set them to, so this becomes the power of each loop, so it's makes a big difference to the size. There we're getting something that's a little bit easier to see. It looks to me like we might, yeah, we're only getting the final step, so I was wrong. We actually need to merge each iteration. Here we go. So now you can see all the stars. They're not very clearly because they're all sitting on top of each other. A way to make them a bit clearer to see is if we use the either polywire or wireframe. Let's stick in polywire and reduce our radius. You can see how we're getting something that looks a little bit like a fractal. What we can do here is use our for each count in our wire radius. We're outside the block now, so we don't have access to this anymore, but what we can do is write it into an attribute. So we're going to create an attribute on here. We can assign it to points, and we'll call this loop, and we'll give it the value, same as we've done here. We'll give it the value for the iteration. So we can just copy this one. So here we have a loop value, which in this case is 2. Let's go to the end. So now we've got 0, 1 and 2. This wouldn't work if we were feeding back each iteration, because every time it went through the attribute create, it would simply change that value. But because we're merging each iteration, then we have the results of the first and the second and the third loop, and each of them is going through this individually, so it's adding these values on. So now outside our for each loop we still have this value loop, which we can use to change some stuff in our object. So we can use it to set the wire radius. So let's make this the size multiplied by that loop. Is it going to let me do that? It is, except it's done it the wrong way around. So the values are getting higher. So let's multiply it by 3 divided by that loop. And now you can see that these values are getting smaller the further we progress. Let's make it all a little bit smaller than that. Right, let's use our power again to progressively, as at the moment it's quite hard to tell the difference, so the power will give a more extreme variation from thick to thin on our radius. Let's try 0.4. Use exactly the same setting again. Loop. Looks like that's a bit extreme. Let's multiply it by 0.1. There we go. So now we're getting something quite interesting. And we can also use our iteration to change the colour. If we do random from attribute and call our attribute loop. And you can see we get a different colour for each pass. So now it's quite clear to see what's happening each time the star runs through the loop. Like these are tiny bits in it. Here we go. So now I can add a few more loops. Probably not very many though, because it's going to get quite dense very quickly. Try one more. Yeah, I think that's going to take too long. I'm going to quit out. So I'll do 4 iterations. We're using essentially a 2D object here, but this would work equally well with a 3D object. Let's drop our iterations down, just in case it's too much for us, and put in something quite simple. Let's try one of the platonic solids. So if we stick in a tetrahedron, that's pretty interesting. So you can imagine this is something that you could play around with for hours. I'm going to leave the tutorial there and let you experiment with loops on your own. It's a really powerful tool that you'll find that you use a lot once you get used to them, both for simple and complicated networks. So I hope you've enjoyed this tutorial. Please subscribe below and leave a comment. Thank you.